Welcome back to another episode of Data Dynamics, where we explore the intricate world of data systems and integration. Today, we're diving into some of the key challenges and solutions in data processing, particularly focusing on event ordering, causal dependencies, and the evolving landscape of batch and stream processing. Whether you're a data engineer, a software developer, or just curious about how data systems work, this episode will shed light on some fascinating concepts that shape our digital interactions. Let's kick things off by discussing a significant challenge in data systems: managing the ordering of concurrent events. In many situations, events can happen at the same time and are often processed in an arbitrary order. This can lead to complications, especially when causal dependencies come into play. Picture a social networking service where two users have just broken up. One user unfriends the other and then sends a message to their friends, hoping that the ex-partner won't see it. If the system processes the message before the unfriend event, it might mistakenly notify the ex-partner, creating confusion and frustration. This scenario underscores the importance of accurately capturing causal dependencies. To tackle these challenges, we can employ several strategies. One effective approach is using logical timestamps, which can provide a total ordering of events without needing coordination. However, this method still requires us to handle events that arrive out of order and involves passing around additional metadata. Another solution is to log events that capture the state of the system before a decision is made. By assigning unique identifiers to these events, we can reference them in future events to maintain those critical causal relationships. Additionally, conflict resolution algorithms can assist in managing unexpected event orders, although they may not fully address actions with external side effects, like notifications. Next, let's shift our focus to maintaining derived state efficiently. This process involves ensuring that data is in the right format across various outputs, which requires a mix of consuming inputs, transforming data, joining, filtering, and aggregating. Batch and stream processors play vital roles here. While both share some common principles, the key difference lies in how they handle data. Stream processors work with unbounded datasets, while batch processors deal with finite inputs. Interestingly, the lines between these two types of processing are starting to blur. For example, Apache Flink integrates batch processing into stream processing, allowing for greater flexibility. However, each method has its own performance characteristics. Batch processing often favors deterministic functions that treat inputs as immutable, which simplifies reasoning about data flows. Now, let's delve into the concept of derived data. Both batch and stream processing are essential for maintaining derived views. Stream processing enables real-time updates, while batch processing can reprocess large historical datasets to derive new insights. This capability is crucial for evolving systems to support new features without disrupting existing functionality. When we think about schema migrations in data systems, we can draw parallels to historical changes in non-computer systems, like the evolution of railway gauges in 19th century England. Just as railways had to adapt to different gauges without shutting down operations, data systems can transition to new schemas gradually. By maintaining both old and new schemas simultaneously, organizations can test new structures while ensuring continuity for existing users. This gradual evolution is also reversible, providing a safety net if any issues arise during the transition. By allowing for a phased approach, organizations can move faster and more confidently in improving their systems. Let's also touch on the Lambda architecture, which has gained traction for combining batch and stream processing. This architecture proposes running two parallel systems, a batch processing system like Hadoop MapReduce and a stream processing system like Apache Storm. The stream processor quickly produces an approximate update to the view, while the batch processor later refines this view for accuracy. This dual approach leverages the strengths of both systems, but it does come with its own set of challenges. For instance, maintaining the same logic across both systems can lead to operational complexity. Debugging and tuning two different systems can be cumbersome, even with libraries designed to provide a unified interface. Additionally, merging outputs from both systems can become complicated, especially when dealing with complex operations like joins or sessionization. Moreover, while reprocessing historical data is valuable, it can also be costly, particularly with large datasets. This often necessitates processing incremental batches instead of reprocessing everything, which introduces its own challenges. To address these issues, newer systems are aiming to combine the best of both worlds, allowing for both batch and stream computations within a single framework. This integration can simplify operations and reduce the overhead associated with maintaining separate systems. As we wrap up today's discussion, it's clear that the world of data integration is filled with complexities and challenges, from managing event ordering and causal dependencies to evolving data schemas and processing architectures. By understanding these concepts and leveraging the right tools, organizations can navigate this landscape more effectively. Whether you're involved in building data systems or simply interested in how they work, these insights can help you appreciate the intricate dance of data that powers our digital experiences. Thanks for tuning in to this episode of Data Dynamics. We hope you found this discussion enlightening and that it inspires you to delve deeper into the fascinating world of data systems. Until next time, keep exploring and questioning the data around you.